Welcome to the final presentation of Skylight. Skylight is a study executed by the German Research Center for Artificial Intelligence and the University of Bremen. The study goals were defined by ESA, and the goal is to explore the inside of a cave structure on Moon, the so-called Marius Hills Skylight. The parts of the mission is we have to move to the Skylight rim, safely descend a robotic probe to gather data from within the Skylight, and explore and map the bottom of a cave segment inside the Skylight. So we will be under the ground of the Moon. This has some specific challenges. We need to solve the communication to Earth while inside the cave. We have unknown terrain inside the cave, though there are expectations of what to expect there. And we need to ensure safe operation of the robot, so we might not lose the robot at any cost. The mission definitions by ESA were the following. We are at the Marius Hills Skylight. We have a landing zone in blue. We have to move from the landing zone to the entry, which is above around 750 meters maximum. And in red is the expected tube below the ground. The pit is 45 to 55 meters deep, with a diameter around 50 meters. And this is where we have to send the probe safely down, and on the ground the cave should be explored for at least 200 meters depth, so it's this area. On the surface there is a sloped area around the crater. We expect that we should not go there with a heavy rover, but only with the probe. So we need at least two systems, and at the bottom there's a cliff-like structure where we have to go down, and our approach is to tether down that part. We have some previous work in that area. We already did experiments of semi-autonomous lava tube exploration on Earth. The result is seen in the upper left picture, where one color cycle represents 1 meter in height, and we went into the lava tube at the lower side and moved up, and the whole mapped area is around 240 meters inside. On the lower right side is a photo from the tube itself, and this is much smaller than what we expect on Moon. And on the upper right hand side you can see a rover in a tethering experiment. There's a small tether up here over a cliff, and also you can see the star-shaped wheels we propose for the exploration rovers. To achieve the goals, we have three main mission components, which are the surface rover used to move through the crater rim and anchor itself there, and the surface rover then deploys the other systems, which is a tethering subsystem and an exploration rover. The tethering subsystem contains the tethering spool and wired and wireless communication devices, and will serve as a docking station at the crater bottom, or at the pit bottom, and also provides charging abilities for the exploration rover, which is battery powered. In operation, the rover can dock to the tethering system or docking station, and then can recharge its batteries and has a high bandwidth communication. When it's not docked, there's a wireless communication, as soon as it's not covered by stones or something else. The pictures on the right are just example pictures based on our robotic experience with different suspension systems and different wheel shapes. In the end, we will have three main mission phases. The first one is the descent, so how to safely put the exploration rover into the pit. We have the settlement, which is basically the deployment of the base station. And in the end, we have the main phase, which is the exploration phase, which is a semi-autonomous guided exploration. I already mentioned that the tethering spool on the Explorer later acts as the base and recharging station. The deployment is on the lower side of the pit, so at the pit ground bottom, and the surface rover can select the and drive around a bit with the tether attached, and then find a suitable location to detach the tethering module and base station, and then it is ready to start the exploration of the lower part and also of the cave. In the first phase, we can remote control the robot as long there's a direct communication or direct wireless communication with Earth. And later we expect the communication to be dropped or shadowed by rocks or corners in the cave or any other means. So we expect to lose communication at some point, and therefore we have adjustable levels of autonomy. So the first level would just be regain communication once it's lost, so the robot would plan a path back to a place where the communication was last detected. And in later phases the autonomy can increase by exploring, setting single exploring goals, which are explained later in these slides. And at the same time we have an adjustable safety. In the autonomous path planning has some parameters like maximum steepness the robot is allowed to traverse, and also the maximum roughness of the terrain the robot is allowed to move into. Also we can have a simulation-based evaluation of pan plus, so before the robot is actually executing the movement, it can be pre-simulated to see if there are some difficult areas. The tethering will be an active tethering. That means while the rover is moving down, the wheels can be used to actively steer around obstacles or to overcome overhangs. So we are not always hanging on the tether itself, but the robot helps to have a safe traversal down to the crater bottom or pit bottom. The tethering spool is, as I said, attached to the exploration rover itself. This means that the tether is not constantly dragged through the regolith or over cliff edges, and mainly so there's minimal movement on the tether. After detaching the base station or the base station, the cave exploration strategy is as followed, as depicted here. So first of all, when we are not having remote control, a goal is set where the robot should move to based on the maps we have from the robot. The robot then plans a path to reach that goal. After the path planning is done, there could be a simulation step, but does not have to. After this, the robot moves to the goal position, and at the goal position it can update its map based on new sensor values. And in the initial phase, after updating the map, the robot is moving back, uploading the map to Earth. Then the operators on Earth can select a new goal, and then the cycle begins from the beginning. If in later phases there can be a more autonomous exploration mode where we leave out the lower part, and after the map update an algorithm selects the next goal. And when doing this, we don't have to move back all the time into communication, but we can let the robot explore the cave by itself, and after a given time, or when a given volume is fully explored, the robot moves back to communication and uploads its findings. For the mission safety, the exploration rover is mapping constantly and also uploads new maps, and we can generate a simulation environment based on the map. And that means the robot can constantly have a simulation running beside the actual movement or before the actual movement, and check whether the planned path is feasible and safe enough or not.